Good morning. Good morning. Welcome to our second day here at ECAS. I'm Fay Collier, and I'm here to introduce the keynote speaker for the morning. So we'll get started here. If everyone could take a seat, find your places. It's my pleasure to introduce Rob Gregg, who will be talking on a subject that's evolving for many of us toward certification by analysis for flight characteristics. I've got a bio for Rob. He's the chief aerodynamicist, principal senior technical fellow, located in Washington State in the United States. So in his capacity, Rob is responsible for strategic direction of the flight organization. He leads the computational fluid dynamics activities across the enterprise of Boeing. And he's also leading predictive flight characteristics efforts and chairs the enterprise wind tunnel capability steering team. Rob received his Bachelor of Science degree in Aeronautics and Astronautics from the University of Illinois, and that was 1978. He began his career at the Douglas Aircraft Company, and in the division of McDonnell Douglas that same year. In 1984, he received his Master of Science in Aerospace Engineering from USC, University of Southern California. And he moved to Seattle to support Boeing commercial airplanes, and that was 2011. And he has 44 years of experience in these various roles. So without further ado, I'd like to invite Rob to take the stage and deliver the keynote this morning.
Thanks, Fay.
Thanks very much.
Well, good morning. I've got about 25 charts that I'll go through. I wanted to spend just a few moments on even the title, as you see, Toward Certification by Analysis for Flight Characteristics. There's a couple of keywords there. Towards, we're on a journey, so we're heading in a path to accurately predict flight characteristics of aircraft. You add in certification to it, and it certainly raises the bar. It's a very lofty goal to achieve, but it's something that's absolutely necessary. And flight characteristics is more than just aerodynamics. It's you have an airplane that bends. Obviously the wing is going to bend. The flaps tend to change deflection. Leading edge devices change position as a result of those loads, and so you have to account for all of that. But you also have power effects that need to be accounted for, and you have a lot of moving surfaces. And so when you talk about prediction of flight characteristics to a level to say you can do certification, you can show compliance, is quite a statement. It's not something that's going to be simple, and it's going to take some time, but we are going down that path. It's absolutely necessary. Part of it is that if you have the ability to do that, that means you're going to design a better product, a safer product. You're going to go into flight test without surprises, and you're really going to end up just validating that aircraft in the flight test phase. So with that, let's go ahead to the presentation. This is the material I'll cover. I'll give you a little bit of background on the journey we've started a number of years ago, what it means when I say certification by analysis. What is the problem statement we're actually trying to solve will be a part of this. Some pretty interesting advancements in computational fluid dynamics need to be touched on, and then we'll kind of cover what is the industry doing, what are some of the NASA activities that are related, and really talk broader about the community of aeronautics to try and gain some momentum in this area, and I'll summarize. Whoops. Wrong way. Okay, it started back in 2017. There was a panel discussion in Atlanta at the AIAA conference, aviation conference. And the premise of the discussion or the panel was that numerical methods are improving. They've had dramatic advances. We design all of our external surfaces using these CFD tools. They will continue to evolve and improve. And as you go through here, you'll see that really, if you look at the progression, you have to come to the conclusion that eventually we're going to be relying more and more on those computational tools to do the certification. So it was really kind of a discussion about, okay, what do we need to do to kind of prepare for that? And is it possible? So there were a really good discussion, and these are the outcomes of the panel. It was, if we're to do this, we need to have kind of a standard process. We need those recommended practices so that there's a consistent way that we approach the problem, and one that really makes sure that we're addressing the issues to be able to convince ourselves and the regulators that we have a good validation of our processes and that our predictions are trustworthy. But the other piece of it is that if we really want to do this correctly, we need to understand the uncertainty of our predictions. And so there was quite a bit of discussion about uncertainty quantification. The other aspect that we kind of came up with is that there is room for an industry group to be looking at some of the foundational validation cases that we should be really trying to gather a lot of important and key data around certain ground test or ground-based testing configurations, and try to link that to, all right, are we understanding the physics associated with it? And do we have, at least when we talk about wind tunnel test results, that we have a way of validating the approaches we're talking about? And then where are those technology gaps between what we can predict and what we can't? Other part of it that I wanted to kind of cover is that there's some trends right now that I think are really kind of converging on this topic. The first is, and I think you heard Lynn Hopper talk about this yesterday, and that was model-based engineering, which really is a V&V activity, and there's the physical world and the digital world, and how do you pull those elements together? If you really want to do this right, you need a reliable set of tools to be able to make your predictions, to know that you're satisfying the requirements. And so that's kind of a desire, but it's also traceability of the process you follow and making sure that you have all the pieces connected. So you know the geometry, you know what's the basis of that prediction, what's the details of the particular tool that you used, and it's well-defined and certainly well documented. Another aspect is that computational fluid dynamics is having some very interesting advances when we talk about scale resolving computational methods. It's showing the ability to do a much better job of predicting the physics. When you get to some of these complex configurations, high lift in particular, you find that there are limitations to the current set of Reynolds average Navier-Stokes tools. It really can't predict very well the smooth surface separation associated with a lot of the high lift critical conditions. And we're seeing a lot of advancements in that. The picture actually is a 787 with a wall model LES solution kind of put on top of it, and it is representing that condition. So there's a lot of really neat things going on with the computational tools. And then the other part is that computer technology, we sometimes refer to as high performance computing, is also seeing continued improvement. And while we thought that the Moore's Law was going to be slowing down, we're actually seeing that it's continuing. Now it happens to be with things like graphics processing units And so you have to be able to utilize those advancements in the computer capabilities. But we're seeing some pretty dramatic improvements in the ability to predict these more complicated flow solvers. So there's certainly a lot of things going on that's helping us go in this direction. So now a little bit about certification by analysis. The FAA, and certainly this is true of EASA regulations, there's hundreds of different requirements that we have to satisfy. Those are all spelled out. They give a lot of information about those conditions that you have to be able to demonstrate and show compliance to. There are different ways of doing the compliance, and that chart on the right kind of has a number of those. And if you look down that list, there's flight test is one of them, but there's also what's called MOC, which is means of compliance 2. Sometimes we refer to it as Mach 2. Not to be confused with speed, it is a means of compliance that's using analysis or calculations to show compliance. And so you really kind of get to the point of, well, what does that really mean? And I'll talk a little bit more about and show you some examples of this. When I talk about analysis, though, analysis isn't just CFD. It can be wind tunnel, it can be previous flight test, it can be flight testing of the current configuration, the one you're trying to certify, and you're making corrections to the condition. It really is anything that is not specifically the flight test point that's called out in the regulations. Then anything that is a correction or an adjustment is partly from the analysis. What allows us to do this, if you look at this is just one example of one of the regulation. You see the underlined area which says, well, the first part of it says by tests. It's required to be by test or by calculations based upon and equal in accuracy to the results of testing. And so that's a rather, it's not a very long statement, but it is certainly a challenging statement because you have to understand, it kind of goes back to the uncertainty quantification is, do you know what your tolerance is? Do you understand what the uncertainty of your predictions are? And can you show that it's within the accuracy of the flight test results of previous products? The other aspect of it, and I kind of mentioned this before, is that this includes numerical methods. It includes flight simulators. So if you can show that, when you have a pilot in the loop simulation, that you can show that it's going to satisfy those requirements is another means by which you can use analysis in this case. And a showing of compliance can be a combination of any of those different analysis tools. Another aspect of it is that it could include margins. You could say, I'm going to be conservative and I'm going to take away some capability just to be on the safe side. So it really becomes a very interesting discussion. I shouldn't say interesting. It really is a balance between what do we know, what can we prove, and then what's safe. So I threw in this chart kind of at the last minute, but I think when you talk about certification by analysis, you have to recognize that different people are going to react in different ways to it. And for those that actually are showing compliance, the very first thing they do is say, where appropriate. You're not going to do this in a case where you're not comfortable doing it. You can't prove that you can do it. You don't have any validation data. You're just not going to make that kind of commitment and try and convince then the regulator that this is a valid approach to follow. So right away, you need to kind of put where appropriate. And there's a lot of other things that go along with that question is, okay, what flight characteristic are you trying to predict? What's the regulation? And what is the regulation? There are some regulations that do not allow you to do it by analysis. But where it does, how do you convince yourself that it's the appropriate thing to do? Are they corrections, as I said, to a current development program? Are they small changes on an existing certified product? Are they, can you do a correction to a simple derivative? and how far are you willing to how much of a difference are you willing to make the case that you have a validated approach. And then you can go on all the way down to the last line, which is, I'm doing something very different than what I've done before. Should I even trust my CFD results or my predictions? I don't want to preclude it to be just CFD. But you really have to be asking yourself, is it appropriate? Do I understand the physics? Am I introducing something new here that I don't understand or may not understand? And be surprised when you get to the flight test. So the goal to accurately predict the flight characteristics and validate these characteristics in flight, we've used the term right at first flight, so you really have that accurate prediction going into it, and I want to just see it being a validation of those predictions, and right for the right reason. And what I mean by that is that we have seen cases where tools for compensating reasons are giving you a right result. I'll use CLmax as an example, but for all the wrong reasons. We have examples where Reynolds Average Navier-Stokes tools will give you a right CLmax, but it stalls outboard instead of inboard. And so it really has completely wrong characteristics associated with it when you really look carefully at it. So you want to make sure that you understand the physics behind it. You want to make sure that it's giving you the answer for the right reason. Here's a couple of examples, and I'm sure that Airbus and other airframers do very similar things here, is we have to certify different antennas. As you can imagine, the airlines are often asking for more and more capability for whether it's Wi-Fi, whether it's for entertainment, whatever it may be. And these are fairly well understood antennas or options for the airlines, and yet we have to go and put them on the airplane and certify them. And it may be we certified it on one version of the airplane and we have to certify it on a different family member. But it is very common to go and actually do a calculation and show that there's no effect on any of the primary characteristics of the airplane. And that's been an accepted means of compliance. And so here's an example of using certification by analysis. Now, generally what it does is it says you just don't have to go to the dive speeds, but we're continuing to improve the methodology so that it's getting better and better, but you wouldn't expect these in most of the positions, at least on the airplane, to have much of an effect at all. Another example here is minimum unstick. You probably have seen photos or movies of some of these types of tests where you do an early rotation of the airplane and it kind of sits on its tail. Our testing, there's usually a railroad tie associated with it. That can be quite exciting, but it's necessary to know what is the airplane capable of doing. It kind of lumbers along and then eventually takes off, and that's the VMU. We typically do that at a number of thrust to weight ratios, and the higher the thrust to weight ratio is, the sportier that flight test condition gets, and to the point where it's hard on the pilots to control that as much, because it's a pretty, at the high thrust to weight ratios, it's going to be a pretty sporty vehicle. It's going to react very quickly. And how do you make sure that the airplane doesn't hit hard? So for safety reasons, we actually proposed eliminating some of those high thrust to weight ratios, take a conservative trend curve and marry it to actual flight test results for the minimum thrust weight ratios. And that seemed to be a pretty effective way of going about that. And since it's a safety of flight issue, it actually is a really good example of why you might do this kind of stuff. So let's talk a little bit about the problem statement. And I think some of you would be pretty familiar with a chart like this. This is the flight envelope of a typical airplane. And we do a lot kind of in that middle area where we think we have a pretty good capability of predicting the characteristics of the aircraft. As you get to the corners of the envelope or the edges of the envelope, which is where most of the certification requirements are, it is really difficult to predict that. I talked about you have to account for air elastics, you have to account for whatever the flight control systems might be doing to adjust for some of the loads, for instance. So it really begins to point to an area of that envelope that we don't do as good a job of predicting, and quite honestly, wind tunnels don't do a very great job of predicting. So those are the things we really need to start focusing on. I think in the past we've kind of said, well, that's difficult to do, so let's kind of do the best we can, and that's good enough. Well, I think we need to now go a little bit further and really try to solve those, and I think we're getting there. It's also clear that the RANS tools are not capable. Well, I might get argument from some of my turbulence modeling friends, but it's really showing that the use of a turbulence model with RANS, it has limitations, and really something else is needed. This is kind of giving you an idea of the complexity of the flow field. You see, well, these are obviously computational results. You see on the upper photo, or image, complex flow field around the nacelle, the edges of the slat. You have a lot of separated and vertical flows that are occurring. And all those have to be resolved accurately enough to make sure that you're accounting for the impact or the effect of those items. It's geometrically complex, and so how do you make sure you have adequate definition of the geometry? We've actually, over the years, have continued to refine the geometry as we do more and more calculations, and so that's, you really have to get the computational geometry as accurate as what you're flight testing. And you have to go through a number of things to make sure, are you adequately resolving the mesh? Are you getting the kind of convergence of the solutions? How accurate are you physically modeling the effects? So in general, I think we found that there's an inability for reliable smooth surface separation calculation. And so that kind of led to a description of well, CFD and CFD. You probably have heard that a lot of times, that there's this arbitrary CFD tool, but there are different levels of assumptions in the equations. And what we're using typically today is a RANS set of tools, Reynolds average Navier-Stokes. There's one level above that, which is, if you're looking at pyramid, it's an unsteady Reynolds average Navier-Stokes. And then above that, which is just becoming online, are wall model LES and hybrid RANS LES. And they're showing some very interesting progress. And then there's room above that if you really wanted to do a complete numerical simulation. It's going to take a while on that Frontier machine that I was showing just to get a solution. And I think some people aren't even sure that you would be able to do it for a complex configuration like that shown below. Whoops. So as I said, the RANS is the workhorse. That's where we spend most of our effort. And for cruise configuration, for where there's very minimal separation, which is what we're designing for, we do a really good job with Reynolds average Navier-Stokes. But when we get to complex configurations that have a lot of interactions, it's not so good anymore. So this kind of gets to, there's been a series of high lift workshops run by AIAA, and some of the information that you can get from that is, one, it shows that, yeah, we kind of peak with Reynolds average Navier-Stokes. There are some things you can do to improve the accuracy, and that is what we call verification, where you have gone through to make sure that what you've programmed, the equations that you're solving, the turbulence model is done correctly, and there's test cases that you can go and run on that. And one of the things this high lift prediction workshop did is it says if you do that, actually the uncertainty around the final result can be reduced. And what you see on the chart on kind of in the middle on the right-hand side is that scatter from the unverified tools, but it actually tightens up quite a bit when you go to the verified, but it still shows that there's a shortcoming. Recently, we're seeing from the high-lift prediction workshop that these scale resolving methods are actually getting the right answer for all the right reasons. I mentioned earlier that in one case, we have seen where you get the right CL max, but it separates outboard instead of inboard. Well, the scale resolving methods are showing it stall inboard and not outboard, and it's getting the right CL max. So it's really beginning to show not only CL max, but the right kind of pitching moment break, the right kind of drag change. And so it's doing a much better job and actually within the accuracy of flight test in many cases that we're looking for. So there's a lot of very interesting results that are showing us great promise. It's now a matter of how do we make sure that we understand how to use that tool, and it's capturing all the physics that are necessary. And so there's still a need for high quality, kind of a database of a common open geometry. And I'll talk a little bit more about that later. The other thing I wanted to highlight, and I don't know how many of you are actually familiar with all the CFD stuff that's going on, but there's certainly a CFD Vision 2030 that was published a while ago. This is sponsored by NASA with all the participants that are shown on the bottom. But it shows, one of the conclusions is there's a number of challenges that we're going to have to get through. And that really set a roadmap as a part of this on the direction we should be going to advance the predictive capabilities. Along the way, and I mentioned the panel session in Atlanta, the outcome of that panel session is we created a community of interest. There was about 120 or so participants that worked with us as a industry community, and we created this document, what we call best practices. It's an AIAA document. There's a reference down on the bottom. But it was published, it was started in 2018 and published in 2021. So that was actually a good amount of effort to get there. One of the things that we found as we went through that community of interest with 120 some people is we all use the same terms with different meanings. And so one of the key findings from that is let's have a common language. And so it really helps, that document really helps to begin to get that kind of common language. It also goes and shows a lot of examples and supporting data or supporting appendices of some of the different issues, uncertainty quantification, a quick explanation on the CFD side. So it's a lot of good information, and if you haven't seen it, I would suggest you go and get a copy. And then there was also from NASA again, there was I'll call it a Vision 2040 on certification by analysis. And again, it shows the roadmap associated with trying to get to a very predictive capability that we're after. So this is a chart that kind of describes what we thought were the key elements of a rigorous process that you should be following when you're using certification by analysis. And there's kind of a foundational piece of it that is, do you have control over that process? So do you understand what the geometry is and you can track that? Do you have some form of quality metrics to make sure that you're getting good results? What is all the information around the particular tool you're using and how you used it? And so that's kind of a fundamental piece. I'll add to that an important part are the people that are doing that, are they actually trained to follow that process adequately? So the second step is model verification. And I talked a little bit about that earlier, in that you need to know that the equations you're solving, the analysis you're doing, is doing it correctly. And so what are the test cases to make sure that your process is doing what you expect it to do? There's a third point, which is, all right, for this particular application, have you validated or verified that it is capable of doing that? Fourth step, model validation, is what are the test cases that you've done to say, I can believe the result. I have a set of good test data. It could be flight test. It may be a combination of wind tunnel and flight test. Whatever the combination of information you're using to show, I have done my homework. I have the predictive capability that are representing the physics. I'm confident in the ability of the process to do this problem. Then there's a justification of analysis adequacy. Why should it be able to predict what you're trying to predict? So it's kind of a, you're putting the story together to say, why should the regulator believe this process? Why should they believe that we have a real predictive capability? And then, as I said, there's a number of other topics in that document that we put together. So it's, I think, a very helpful way of looking at the problem associated with using certification by analysis. This is just an example. Obviously, it's an eye chart. You're not going to read all of it. But this is an example of the roadmap that was put together for the Vision 2040, the Cert by Analysis Vision 2040. It really does summarize that it's an integrated system. And there's a lot of elements that need to go into this so that you have that confidence in the ability to predict it. You have all the insight you need to make sure that when you're looking at the physics, when you're looking at something maybe a little different from the last product, that you know you're going to capture the characteristics properly. And then, as I said, uncertainties are all part of that. So it's a really good document to read through if you have an interest. There's a lot of meat to that document. And then there's what was called the technical challenges associated with predictive flight characteristics. So the first part of it is, how do you validate it, at least based upon wind tunnel testing, ground-based testing? And that's kind of fairly straightforward. I think we kind of know how to do that. And in fact, we're actively doing this, and you'll see kind of that ecosystem that developed as a result of this thinking. But then there's a second point, which is when you start talking about multidisciplinary validation, what does that look like? When you're tying computational fluid dynamics to aeroelastics to an engine simulator, how do you prove it's all working correctly and validate it? It can be ground testing, maybe it's a scale flight demonstrator. There's different ways to do that, but we have to think through what's the best approach to do that. And finally, the grand challenge is, how do you actually prove something in flight test? That you've predicted it, you go and do a wind-up turn, and sure enough, you've accurately predicted the characteristic that you're seeing. So those are the elements around how you step through this. And we'll talk more about that a little bit later. I mentioned the ecosystem. This is a common research model that we've been, it's actually been around since 2018. And it's being built by multiple organizations. I'll kind of show the entire image of all the different things being done. But it's an open geometry. It is something that is you can find on a server at NASA. It's available to everyone. It has all the basic geometry. It's used by the high lift prediction workshop. And we're planning on doing a lot of additional wind tunnel testing, including getting information on off-body flow features. And so there's a lot of organizations and teams working to build a number of models and get the kind of information we're looking for. And as stated on the chart, there's 12 different organizations across the world, US, UK, France, Germany, and Japan that are working on elements of this. This is kind of that big ecosystem plan. And you see over on the left-hand side all the different teams that are doing wind tunnel test configurations and have wind tunnel test campaign associated with it. There's a timeline that shows when all these different tests are going to occur, and there's going to be a series of NASA tests. We at Boeing are going to be doing a number of tests. Honor has already done some testing on this. And then there's Kawasaki and JAXA who are planning on also doing some testing. Down the middle, kind of middle left, you see all the different areas that are going to be looked at. So it's a reference configuration, so you're comparing how different models and different tunnels compare. You have, kind of, can you do optimization of like a flap deflection? So there's that kind of information that you can obtain. Reynolds number effects, we're going to be going from atmospheric tunnels all the way to cryogenic tunnels. And so we'll get a full range of Reynolds number effects. Wind tunnel modeling effects will be a part of this flow physics, CFD validation. So there's going to be a lot of instrumentation, much more than we would normally do for the type of production testing that we do typically. Ice effects, so icing becomes an important element when you start talking about, how to certify an airplane. Acoustics, trailing wakes, and even propulsion airframe integration. So all those are elements of this ecosystem. So it's, for a number of years, we've been pushing this big boulder uphill, and now it's beginning to have some momentum and falling on its own. So there's a lot of additional people coming on board. But it also requires a pretty massive effort to try and make sure that we tie all of these different configurations that are tested, the wind tunnel models themselves, together so that we understand what are the differences. So kind of to summarize, and I obviously will be leaving a little bit of time for questions. Model-based engineering is really pushing us to get an accurate prediction capability, and so there's an impetus to go this direction, and it makes a lot of sense from our design capability that we improve the methodology to get as much performance, to get as much, to make the products as safe as possible, to even look at some of the failure modes through the predictive capabilities that you would never be able to flight test just because it's a safety of flight issue. So that's an element of it. Numeric methods continue to improve, and I've kind of gone through the sub-bullets there, which is really kind of an exciting advancement that's happened more recently. Computational tools are actually always kind of limit what we can do with our CFD tools, and they're coming along just as quickly as we need them to. So in this particular case, we're actually seeing the ability to get engineering solutions in a very timely amount of time, even though we're going to much more complex set of equations to solve. Obviously, if I hate to admit, but almost every program, well, I'll go further. Every program has an anomaly. We have discoveries in flight test. And part of the issue when we have those discoveries is how do you solve them and resolve those? And what we want to do is move the predictive capability forward so that we don't have those surprises. Those surprises are designed out of the airplane. Certainly now, what that means is that we have an ability to fix those problems when we discover them. And as an aerospace community, we're working towards that kind of comprehensive wind tunnel-based set of data to help validate that we can do predictive characteristics. But a wind tunnel set of data, high-quality wind tunnel set of data, is not sufficient to show that you can do certification. It's necessary, but not sufficient. What we're really after is a trusted certification by analysis process. You have to be substantiated. It has to be a disciplined approach and reproducible. throughout the life cycle of the certified product. So it really is that higher level of confidence in those predictions that are necessary. So I'll finish up with some challenges that we have in front of us. I talked about that we're continuing to do that high quality set of wind tunnel tests and collection of information so that we can validate the scale resolving CFD tools. We continue to work towards characterizing component and system level uncertainties. That was one of the things that came out of the panel session, was we need to understand uncertainty. And so what does that process look like? You can go to a very detailed level. Is that practical and does that really help? So we've got to think through what does that really mean and how would we accomplish that uncertainty analysis. It has to be an integrated process. You can't do this bit by bit. It really needs to be tied together. And so that kind of points towards multiple disciplinary tools, or MBE if you want to think of it that way. But it is absolutely necessary that it's not just one group. It's aerodynamics, it's structures, it's the loads that act on that, it's the control laws. So all that plays into this. How do you develop the validation tests for that multidisciplinary analysis set of tools and process? That's going to be an interesting, we can kind of see how you can do that from the wind tunnel perspective on a rigid model. But now I say rigid, wind tunnel models aren't completely rigid. They're more rigid than the real airplane. But you have to account for the aeroelastics, but they are steady state. So it's a little bit easier job than what's being done on a real airplane. So what are those representative validation tests for multidisciplinary analysis? And then finally, if you really want to do this, the acquisition of an appropriate set of flight test data that is available. And there may be a question of, is that really something the community should work on, or is that really left up to the airframe companies? I've got my opinion. And then how do you build that regulatory advocacy and acceptance? So those are the challenges in front of us. I will say that there's a panel discussion at 10:30. It was, the panel consists of many of the same people that were part of the Atlanta panel. So I'm looking forward to that panel session at 10:30. We'll be talking about many of these challenges and many of the other aspects of certification by analysis. So if you're interested, certainly come back here and we'll talk about that. And I'm going to open it up to questions, but first I'm going to describe a little bit about this photo. It's kind of a neat photo. You see a vortex being shed from a nacelle chine. Fairly well behaved. It's following the surfaces of the wing fairly well. You see a refraction through the sun, and you also see a shadow off to the left. The interesting thing to be thinking about when we talk about certification, this is kind of a nice, well-behaved condition. I'll say that the flow is happy, the plane is happy, and the pilot is happy. You go up a little bit in angle of attack, and that shed vortex from the chine just kind of starts to deviate from the trailing edge of the wing and just kind of says bye. At that point, of course, the flow is very chaotic, and we're talking about being able to predict that. And you probably can see what I'm going to say now is that the airflow is unhappy, the plane is unhappy. An airline pilot would be unhappy. If we've done our job correctly, he will never get into that condition because we understand the limits of the airplane. A flight test pilot, though, might be happy. Once he recovers, he'll probably smile and say, let's do that again, and again, and again. So with that, I open it up.
Thank you, Rob, for that excellent tutorial on this very complex subject. I learned a lot, And as moderator, I'm going to exercise my privilege to ask the first question.
Sure.
So my question has to do with uncertainty and propagation of uncertainty through this process.
Yeah.
And how at the end you account for all of that stuff and report out on that. So what's your thinking along those lines? And then we'll open the floor up.
So that is a kind of a hot topic. We have had discussions about what does that uncertainty analysis look like, and how do you account for all the variability of, it could be geometry, it could be the numerical methods, and how do you collect all that uncertainty and make something that's actually useful. I can imagine going to the regulators and saying, well, I'm 98.7% certain of this answer, and I'm not sure that's going to help me a whole lot in substantiating that I'm confident in this solution.
Yeah. But last year it was 95.6%.
It's getting better.
So this is better.
Yeah.
Okay, thank you. Let's open up the floor. I think we'll go for maybe 5 minutes on questions. I need to call Axel up before we depart for some cleanup and some announcements before we start the rest of the day. So let's take some questions for Rob. And we're having a hard time seeing up here with the lighting. So we do have people that will be helping with microphones. And if you have a question, please identify yourself.
Yes.
And then ask the question. Thank you.
Thank you. Bruno Stoufflet from Dassault Aviation in France. So thank you for your comprehensive presentation. That was very interesting. I assume that the objective, maybe the major objective of this activity is to limit or reduce the number of flight tests necessary for the certification at the end. So can you comment on the achievements on that as of today, or the foreseen achievements that you may hope in the future?
So to put it succinctly, the answer is yes. We do a lot of testing, and a lot of that testing is stuff that if we had done the homework up front, we probably could have avoided. I'll just kind of give you a tantalizing comment that we are already today using some of these advanced CFD tools to solve problems in flight tests that we were not able to solve using RANs. And so it's already showing that it's invaluable to solving both on the military and the commercial side some of these very difficult problems that we would, in many cases, would not be able to identify in wind tunnel testing. And so right off the bat, if you're able to go in and actually get to the real flight testing that's used for certification, you would be saving flight tests if we had incorporated that earlier on in the design case. Long term, I think that if you got to a regular cadence of doing validation of your predictions, at some point, when do you start to say, okay, we've done enough? Maybe you reduce the amount of conditions you do. Maybe you focus on the areas where you don't do very well only. Well, I shouldn't say only. You're gonna spend more of your time in the areas that you have the largest uncertainty based upon what you're seeing. I do think it would make for a much faster flight test program, and that's going to be quite substantial benefit in the long run.
I think we got a question over here to the right.
Good morning, Rob. This is Mehdi Koramil, NASA Langley. Excellent presentation. I'm going to raise an issue which I've raised with Mujib Malik, and I'm going to raise it with you. Could you elaborate who is putting together a realistic engine, like a CRM model that we can use for some of the validation, and who is going to be testing that, putting out the experimental data? Because 2040 is not that far from us.
So what we have for the CRM today is just a representative nacelle. It's not the internal workings of the engine. It would be interesting to try and create a common research engine model that you could go and do something with, but currently that isn't something we've been focused on. Maybe not the greatest answer for you, but that's where we are.
Rob, looks like we have a question from Rich over here.
Hey, Rich.
Really just an extra comment. We've tried to have a common research engine and gotten several propulsion companies together, but we haven't yet come to that open, public, relevant geometry that's been able to be shared yet. So it's not for lack of trying.
Thanks, Rich.
Yeah, there we go. Hey, Rob, excellent talk.
Hey, Mark.
Yeah, and I think this is a fabulous topic. I'm very excited to see so many of the research institutes led here by NASA doing this work and coming together, building on the CRM type of mentality and spirit. Something occurred to me as you were speaking. You know, the way we do Flutter certification today is interesting. We don't go anywhere near the actual condition. The actual condition has, crazy.
And there's a reason for that.
Yeah, that's right. No, but it has crazy servo aeroelastics. It has crazy transonics, unsteady transonics. But we've convinced ourselves we can do it. We've convinced ourselves it's okay to just go up and give a stick wrap or have a little exciter on the wingtip and look at the damping decay with speed and stop. And I wonder if that might be a model for how we could. It's already done. We already certify by analysis virtually all of our Flutter. We don't really test anything except the incipient damping. And I wonder if that could be a model for what you're trying to do here more broadly.
Yes, it can be. I think we're trying to actually go a bit further because the fidelity of those tools can also vary, right? So we're trying to make sure we pick up all the details of the physics going on. Now, certainly when you do wrap tests to what are the frequencies, what are the modes of the structure, and then go and demonstrate that it damps appropriately during the flight test program, you've defined what that envelope is, and you're going to go and make sure that you're acceptable within that range. I think it's a little more difficult from the flight characteristics standpoint because, as you know, when you get into stall, you can get some very interesting characteristics that the pilot has to deal with. And so it becomes a little more difficult. So that, to me, is a little different kind of a problem. There are elements, though, that we could follow what the loads community does.
Rob, I think, are you okay with one more question? I think
Sure.
we have time for one more. And I think
so.
there's one in the queue down here.
All right.
So, hello, my name is Ramon Lopez Pereira. I work at Saffron. So the question from my side is, we're talking a lot about RANS modeling. Is there a consideration going for another type of solver like Boltzmann, for instance, a lattice Boltzmann, where you can add the turbulence directly into the equation instead of having to model it? Mandatorily for a RANS, you need to model it some way, but for the Boltzmann, you may just introduce the turbulence in the equations and not need to model it. Is that considered in the working group, or is maybe not feasible for a short term? It's more a very long-term approach, or?
So the answer is yes. Scale resolving does include, in my mind at least, the lattice Boltzmann, for instance. So that is a part of this, and what we're trying to do is acquire the wind tunnel data to go and make sure that we know how to use those tools and that we're getting the right physics. And so that's the need for getting that high quality set of data from multiple facilities, at multiple Reynolds numbers and multiple configurations. And so that it doesn't preclude any type of CFD. One of the things we didn't want to do as part of this best practices was dictate the tools that you use. We wanted to really get to what is the validation data you need, at least at one level, which is the ground-based wind tunnel testing, and then kind of leave it up to the airframe companies to take care of it from going from that basis to actual flight test results. But it doesn't preclude any type of CFD. I did talk mostly about RANs because that was our, our standard process up until recently.
So Rob, really like to once again thank you for coming, enhancing our experience here at the Congress. We have a small token of our appreciation.
Thank you.
Newly minted medallion for 2022.
Excellent.
And excellent job. Thank you very much.
Thank you.
So before we depart, I'm going to call Axel Prost up. He's going to give us a little bit of cleanup for the rest of the morning.
Thanks a lot, Faye, for introducing me. Thanks for the excellent talk. Even I, as an ex-pilot, learned something. Thanks, Faye.
You got it.
Good morning, everybody from the Secretariat. Just some quick comments. Today is the big day for the students. So tonight we have the student party at starting 7-ish. Before that, we have the speed mentoring. And our early career committee really put together an excellent and very diverse set of mentors. So I really like to invite all the students to be part of the speed mentoring. It starts at 6 o'clock here in this room, and you will be led through of all the details. Further on, for the banquet on Thursday, everybody who has a ticket and wants to have transport should give us please an indication at information here at level 4. So please come to information and request the seats that you need for your spouse and for yourself, because we need to adjust the buses and have you on the list. If you're not on the list on Thursday, you need to take care of the organization of your transport by yourself. Last not least, following this, we have the interactive presentations, where I really like to invite you to. We have 2 screens up to the left and 2 screens on the balcony. Speaking of the balcony, if they're not used for the interactive presentations, they might be used for sessions. And if you use the exhibition space for your private time, which you are very much invited to, please keep the volume a little bit down because it's interacting a little bit with the session upstairs on the balcony. Enjoy the day, and if you have any questions, come and see us at room 34. Thank you.